Afternoon, my name is Erik Streed. I'm Deputy Director of the Center for Quantum Dynamics. And, okay, there we are. This is work that was done principally by Kenji Shimizu, who is now with CSIRO, as well as Jordan Scarabell, who's down in Adelaide as well, and Mirko Lubino, who is in Italy. So, and supported by Lockheed Martin. So, we use energy, we do useful things with it, sometimes less useful things depending on how much you've been on your phone lately. Looking at global energy consumption, IT is roughly about 10% of that mix, depending on which ways you want to slice it. So as we develop quantum computers, their potential energy footprint is important. We've got lots of different candidates, and they're implementing lots of different technologies, and we've heard many, many talks about different energy aspects of them. So I'm going to talk a little bit about trapped ions, which I don't think we've really heard very much about so far. And in particular, the 2-qubit gate, which is currently used in most labs and most prospective commercial implementations, is something called an adiabatic sideband resolved gate. So this is where you use some lasers to tickle the vibrational modes and use the vibrational modes of several trapped ions as a bus. So you need to take your ions, cool them down to the ground state. That's not a big deal. And then you need to resolve these sidebands. And this means that you are limited by the harmonic motion. So as you add on more ions and become more useful, you get more and more sidebands and their spectrum overlaps. So you can see going from 1 to 2, to quote Biggie, more ions, more problems. And if you want to do computations with progressively larger crystals, then this mode problem becomes pretty catastrophic. There's ways around it by dividing up your problem, but then that slows things down again. These things become harder to address, longer to resolve. But critically, in all of these cases, you need to use non-resonant laser light. You need to use a lot of it because the process is weak, so you've got to have your laser on for a long time. Lasers are expensive, laser power is expensive, and that's what ties in with this conference. So we've been working on a different variation of this, which is the fast 2-qubit gate. So instead of going slow, we're going to go fast. This will hopefully help the fidelity, which maybe reduces your physical qubit count in terms of being able to implement virtual qubits that are well behaved. And so hopefully instead of being kind of microsecond time scale, we can get this down to nanosecond time scale. And that's all great, except the cost that you pay is you need to apply more laser power to get it to go fast. So this works by applying coherent kicks through absorption and stimulated emission. And so if you're going around on a harmonic oscillator wheel, trading off momentum and position, you're kicking up, you're evolving for a little while, and then kicking back down and sort of unwinding the kicks that you've done. And sort of the more kicks you give, the faster you can map out that blue area there and get your phase gate done. So you need to create a series of pi pulse pairs to kick around your atom. So stiffer traps give you better performance. That has basically remained static since roughly the late 1990s when Chris Monroe and Dave Wineland made a push to try to improve trapping frequency, and it didn't really work. So we're generating a state-dependent force, and we're using a resonant process. So even though we need ostensibly more laser power by going to a resonant process, we're getting sort of the maximum leverage from our photons onto our atom. So this is a good thing if you're thinking about the energy efficiency of being able to drive this 2-qubit gate. So because they're fast, we're not resolving anything. We've got a bandwidth of about 400 gigahertz. This is compared to with a few gigahertz or tens of gigahertz in terms of the internal structure. And so we need to use polarization to separate things out. You can improve this further by using metastable state shelving. You get higher fidelity, but then again, you need to use more lasers. And you've got to choose wisely there because not all of your states are going to necessarily be happy getting smacked around with high energy laser power. So we've implemented this in ytterbium-171, transitions at 370 nanometers, so slightly in the UV. We're tightly focusing our beam to get higher intensities. This is running about 300 megahertz repetition rates, about 300 times our trap frequency, and our pulses are about 2 picoseconds. This is short compared with 8 nanosecond excited state lifetime. So that should give us, hopefully on the order of potentially 3 or 4 nines of accuracy before we get an error because we're in the excited state when we expect to be in the ground state. So energy use comparison. So if we're thinking about building a quantum computer using this sort of technology, just to give a comparison with an Apple M1 processor, so that uses about 40 watts of power. It's got 16 billion transistors, is clocking in at 11 trillion operations per second. So that works out to about 4 petajoules per operation. Now for a trapped ion processor, our particular spec, we've got 70 milliwatts of UV at 300 megahertz. Now the electrical power that goes into making that 70 milliwatts of UV is substantially higher. We've got several stages where we're talking about many watts of IR power in that process. But let's put on our happy glasses and just worry about that 70 milliwatts of UV. So that gives us about 400 or 230 picojoules per pi pulse. So we're talking about on the order of nanojoules per operation, which is not super great compared with the Apple M1 processor. And then just as a ballpark, let's say you need 1,000 physical qubits per logical qubit, and people in the audience are much better educated as to whether that's a reasonable assumption or not these days. And this isn't including overhead. So we've got many, many, many orders of magnitude to go. That being said, we're talking about a laboratory device versus a highly optimized modern processor with arguably trillions of dollars of capital investment has gone into optimizing these silicon CMOS fabrication things specifically for this sort of activity. So it doesn't look great, but on the other hand, what's 6 or 7 or 8 orders of magnitude between friends and a few $trillion? So there is hope. This is what our system looks like. We start off with telecom stuff and then do a bunch of different steps. I'm going to skip this because I don't have very much time. We do some pulse switching. We care a lot about our central frequency because at our hearts we're atomic physicists and we want to excite things. Even though we're only detuned 30 gigahertz off on a 400 gigahertz pulse, detuning matters. There's a great trick with Michelson interferometry to figure out our pulse width that we can measure it. We've got a single shot protocol here where we prepare our state, we give it a kick, and then we see what happens to see whether we get a pi pulse or not. Long answer short, we get about 94% fidelity for an individual kick, which sounds pretty good after you've been crunching in lab for a while. But then you get Kenji to do some simulations as to what this would amount to in terms of gate fidelity, which is what people that might actually pay for a quantum computer would care about. So how close are you to your ideal? So is your apple matching your expected apple, or are you trying to look apples and pears, or apples and Clifford, which might have a very low fidelity offset? And there's a couple different processes that generate this. We do these calculations for Dewan scheme, which is a fairly straightforward scheme, and we see that hypothetically we might be able to get on the order of 4 nines off of a relatively simple scheme. And so you're feeling pretty good about life and being able to actually build a quantum computer. And then you look at the noise sensitivity, and then life gets sad. So with our current level of intensity fluctuation, which is about 2%, our fidelity rate is 32%, and I'm not even really sure you could call that a fidelity rate. Certainly nobody's going to publish you on that. If we were to improve things by an order of magnitude, maybe a low-level journal would publish us with an 86% fidelity rate. Getting down to a 0.02 level fidelity, now we're up at 93%, which is okay, but certainly not going to be anything great. If we want to get into interesting levels of fidelity, we're looking at needing to intensity stabilize on the order of about 99%. Or to get 99% gate fidelity, we're looking to stabilize on the order of about 10 parts per million. That gets hard for intensity stabilization. The other sources of noise, things like beam pointing and frequency drift, timing jitter, these are all things that are relatively technically easily addressable, but this intensity noise is a bit of a bugbear. So in particular, if we're thinking about our 230 picojoule pulse, that's only about 400 million photons. It's not a lot of photons. That gives us about a 43 dB shot noise limit. So that gets you 10 to the minus 4 intensity stabilization, which only gets you a qubit fidelity of 90%. Keep in mind, this is on resonance. This is the low power option versus using these off resonant protocols, which are currently much more power hungry, then they can get higher fidelities. In terms of stabilizing this, even if you're detecting all of the photons after your process is part of some kind of stabilization scheme, that will work, assuming that your laser doesn't have a lot of pulse-to-pulse noise. This type of laser does have a lot of pulse-to-pulse noise, particularly at this 10 to the minus 4, 10 to the minus 5 level. And this sort of tracks if you look at what the silicon detector responsivity would be. So there's sort of this fundamental conflict between running laser pulses with low noise and running low laser power. And you might say, oh, but we can use engineered quantum states to get us out of this. So instead of using coherent states, maybe we can use some nifty Fock states or something else that high noon states that people have come up with. That comes with the problem of generating those in an energy efficient manner. And I'm unaware of any scheme that generates non-classical light in anything approaching an energy efficient manner, although I am perfectly happy to be contradicted, particularly by the people over in that corner. And we're starting off with 5 watts of IR. And so I've either gone through this super fast or not super fast. Okay. So the conclusion, so we've demonstrated a 94% fidelity in doing pi pulses and looked at the implications for that to realizing a fast gate protocol to build fast 2-qubit trapped ion quantum computers. This is also possibly useful for some of the neutral atom quantum computers as well. We found that there's kind of a fundamental trade-off between having low noise versus low power. So you can have one or you can have the other, but it's a fundamental conflict that may be a big problem going forward. You can maybe get away from some of these issues by switching to a rapid adiabatic passage type approach. So that's going to be more robust against intensity noise, but has the downside of demands more power. We need to look into how that scales. And possibly there's a pulse sequence magic that we can come up with that ends up being more robust against noise in individual pulses. Again, the fact that the pulse-to-pulse noise variation is where the noise is sitting may kick the rug out from under us, but I would never underestimate the people at places like Q-Control for being able to figure out crafty ways to get us out of these problems. That's it. Thank you very much.
Thank you very much, Erik, for being bang on time. And also a lovely talk. Do we have any questions? Sure.
Your last comment, you said, what was the trade-off again between power and noise? More power, less noise?
Excuse me again?
You said there was a trade-off between power dissipated and noise or fidelity.
Yes. So if you've got more photons in your pulse, you have the potential to have less shot noise.
Okay, that makes sense.
So shot noise, classical. We're not doing anything crafty here. We're knuckle dragging laser people. We're not having crafty highly engineered quantum states.
The interesting thing about that is it's exactly the same trade-off for quantum limited clocks.
That does not surprise me.
Sorry?
That does not surprise me whatsoever.
No. In fact, that little cycle that you're doing in the phase space looks like a nonlinear oscillator or nonlinear clock. So there may be a way to put this in a fairly general thermodynamic setting.
I would be very willing to believe that, and there's certainly a reasonable contention that quantum computers are just really, really, really gussied up atomic clocks.
I have wondered about that at times. Any other questions? If not, thank you very much, Erik.
Thank you.